last minute Nellies out there trying to print out their project. Do you want to get the door first, Kai, please? So you can just put your project in the folder, and I'll make sure I have them back to you minimally by Monday and maybe Friday. Okay, so we're in a new packet now, which I put at the back, and we're gonna be a little backwards today. We're gonna start with our group activity today versus waiting to the end of class. So want to start us off, Coleman?
We now have a lot of experience with certain kinds of functions, linear, quadratic, polynomial. In this chapter, we introduce two new functions, the exponential function and logarithm.
Okay, so we're going to be dealing with exponential functions and logarithmic functions, and that's pretty much the final types of functions we're going to be looking at. We'll throw in what's called a logistic function at the end of this section, but pretty much we're done with the types of functions we're going to look at in this class once we get through these two major groups. Has anybody ever heard the term like something, I can't say it because then I'll give away what I'm asking, the word exponential used in any way in like everyday life or reading or anything? Where have you heard it, Coleman? Exponential growth, right. So in fact, we're going to be looking at that. And in what terms have you heard exponential growth? Has it had, what context? Has it had to do with money or populations or just all of them? Okay.
It grows faster the more there is.
Okay, so Coleman says it grows faster the more there is of it. That's interesting. So Coleman says it grows faster.
Oh, you're going to quote me off of this?
Yes, I think that's a great way to say it. It grows faster the more, what did you say? The more there is of it. And in fact, that's exactly one of the main features of exponential growth. We might say it grows proportionally to the size of a population, but hey, he's got it. All right. So if you got, for example, if you had a growth factor of, say, let's make it easy for our brains, 10%, which would be huge, and you had a population that was 2 million people, and it was growing at 10% a year, say, the next year there's going to be 200,000 more people. If you had 200 people, there's only going to be 20 people. And each year that you're adding, the increase is getting bigger and bigger and bigger because your population's getting bigger. Same with money. You have a situation where you have money that you can invest. So for example, if you happen to be like very young and you inherited like say even 25,000, if you put that away and it earns money at a certain percentage, probably by the time you retired, you'd be shocked at how much money you would have saved. So usually there's a children's book, I think it's called One Grain of Rice, something like that. Has anybody heard of that children's book where there's a peasant and he does something for the king and the king says, I will repay you with any riches that you want. And the peasant says, I just want, he had a chessboard which has, I think, is it 64 squares on a chessboard? So it has 64 squares. And the peasant says, I want, the first day I just want you to give me 1 grain of rice, put it on the chessboard. And the second day I want you to double it, 2 grains of rice. And the third day, 4 grains of rice. And the king is, oh, what a fool this peasant is. This is all that he asks for my kingdom. And by the end of the book, the man's the richest person in the kingdom because the rice is growing exponentially. And one time I did this to one of my kids. I said, so how about if I offer you a job? Well, what's that, Mama? I said, well, what if you wash dishes every night for a month and I start you off and I give you a penny the first night and then the second night I give you 2 cents and the third night I give you 4 cents. No way. So then I sat down. Does anybody have a sense of how much money you would have by the end of the month? Oh, you did?
Yeah.
Why did you look that particular thing up?
I've heard that one before with the pennies doubling constantly.
Yeah, I was going to actually put up a little scenario where I offered you a job where I gave you $1,000 a week for a month or a penny a day for a month. What do you think most of you would have said? You would have taken the $1,000 a week. So at the end of the month, you would have earned what, $4,000? Okay, well, let's see what 2 to the 30th is. We'll even do a 30-day month. Let's take a look at the graph. Oh, let's see. Did I do the table? Let's just put 30 in. 1.07 e to the 9th. So how do I represent that? 1.07 e to the 9th. What do I do with that? I don't add 9 zeros. I move the decimal plate 9 places to the right. So there's 2. So how many zeros am I going to add? 7, because that's all that I have left. 3, 4, 5, 6, 7. So, okay, and that was 2 cents, right? That's turned into a lot of cents. So even if I chop off a lot of 2 zeros here, this is how much money you would have had at the end of the month. So it's really good to have some mathematical literacy if you ever have that job offer. I'd take that versus the $4,000 a month. So anyway, it's a quick little scenario of how quickly things can grow exponentially. And so, of course, my kids thought it was very unfair that once I showed them how much money they would have, they wanted the job, and I said, sorry, too late. Okay, so in your groups, as I said, we're going to start backwards. I want you to do 1 and 2, Roman numeral 1 and 2 in your groups. Then we're going to come back together and discuss it. Here. So we can summarize what you've just worked on, and if you came in late, you can catch up later or just listen now, since many of you came in almost a half an hour late. Okay, let's come back together and summarize what we found. So the first model that you were looking at, the rabbits were growing at a constant rate, 1,000 rabbits per year, and this was the function you came up with, a linear function. The second table that you looked at, the rabbits, remember, were in rabbit utopia, so they were doubling every year, and they started off with 1,000, and this doubling now is our base of our exponent. In this case, we're using t because we're looking at as time passes year by year. So these were the 2 equations you come up with. This is now what we call an exponential function. This is where we're starting today with this idea of an exponential function. Now, if I wrote this, well, let's go through these first, and then I'll show you what I was about to show you. So, what does the 1,000 mean in the linear model? What does the 1,000 mean here? You might say, well, which 1,000 am I talking about? Let's talk about this 1,000 right here. What does that mean? What? It's a constant. And what does it mean in terms of the story that we were telling? Read. Huh? The original population, right. So in the linear model, this first 1,000 represents the original population or the initial population of rabbits. And the symbol that we give for anything that's an initial is we put a little subscript on it with a little 0, p sub naught. Okay, is how we read it, p sub naught or p sub 0 if you prefer. That little 0 always tells you the initial, the original, as Joseph mentioned. What about the 1,000 here? What does that mean? Karen, did you have your hand up? In the exponent. Yeah, this one would have been the growth. So let's go. Well, we're going to get to that. What Karen was answering was this. What effect is the second 1,000 in the linear model? She's referring to this one right here. In the linear model, that 1,000 refers to the growth rate. That's exactly right. That your rabbits are increasing. Remember, it's 2 variables. Increasing at the rate of 1,000 rabbits. There's your first variable, the unit for your first variable, which is your y-axis, or your vertical axis, per, and then whatever your horizontal axis is per year. So you have to see 2 units always when we're talking about a linear function and we're talking about the slope. So that's right. It's a constant growth rate. So the 1,000 refers to a constant. It never changes from year to year. It's a constant growth rate. Okay, so Karen was answering that. So let's go back to A and ask, what does this 1,000 mean for the exponential function? In the linear model, it represented the initial population or the original population. What's it represent here? Same thing, right? So it's the initial population in both models. Okay, in both models, the 1,000 represents the initial population of rabbits. Okay. So what can you say about the rabbit population in successive years using the linear model? We've actually already answered that. It's growing at a constant rate of 1,000 rabbits each year. All right, so that's number 3. So when you graph this, you should have gotten something like this. And notice here, let's find the y-intercept of this equation. I have it also in GeoGebra. Here it is in GeoGebra. And I've got the y-intercept labeled. But I wanted to just give you a little sense of how you work these the spreadsheets here. If you ever want to do this in GeoGebra, have you anybody worked with like Excel in the class? Like a lot of you are business people, right? You worked with Excel. You can work this just like an Excel spreadsheet. In other words, all you have to do is put 0 in here, and then to get this, you say equals A1, because that's the cell, plus 1, and then you just drop it down, and it will give you successive numbers. And similarly here, you can say equals the function's f. You can say f of A1. Put the cell number in, it will give you 1,000, and then you just take your little right-hand corner and drag it down. So you can see Coleman's original idea here is that as the population is getting larger and larger, so isn't the increase here. It's growing faster depending on how many rabbits there were initially. To say something is doubling every year is just an enormous growth rate. I mean, thank goodness our populations don't grow at that rate. We'd be in big trouble. Spread of disease. I had someone in my second class when he was looking for data for the linear regression project. He was looking at currently what's happening with the Ebola deaths in Africa in the spread, and he wrote on his paper. Well, he sent it to me and he said, I better save this for exponential growth. And he was right, because it grows, any type of disease, any virus type of thing grows at an exponential rate. If you think about cell division, the doubling idea, this is exactly cell division right here that you're looking at. And the difference here is that it wouldn't be like one day. It's probably a much smaller time period. This is how we all began, with one cell that then broke into 2 cells, that broke into 4 cells, that broke into, and it just kept going. We just didn't have the 1,000 in front. We had 1. Okay. So what is the y-intercept here on this model? What is the y-intercept? How would I find? What is it? Can anybody tell me what it is? 1,000. And if you had to use this model to figure it out, how would you find the y-intercept? What would you do here? Plug in 0 for t, yep. So you get 1,000 times 2 to the 0, and 2 to the 0 is going to give you what? And then 1 times 1,000 gives you 1,000. So you can always tell if your exponential function, because here would be like the parent exponential function for this model, 2 to the t. This is called the doubling function. Okay, the doubling function. Notice what the coefficient is in front of 2 to the t. If we wanted to put it in, it would just be the number 1. So if I graph 2 to the t, it's going to go through 0, 1, because when t is 0, my function's 1. Notice I did a transformation here. I stretched this by a factor of 1,000. All my y values are getting stretched by 1,000. So my very first point here, instead of being 0, 1, is 0, 1,000. I've multiplied all my y values by 1,000. So anytime you look at an exponential function, the first thing you want to do is to say, has my parent exponential function been stretched in any way or shrunk? And the way you tell that is to look at your y-intercept. And whatever the value is for y is the factor that sits out in front. That's either your stretching factor or your shrinking factor. So the minute you look at an exponential function, that's one key point that you want to look at. And if it's 0, 1, it's just a baby old parent function. Okay. Now the base can change. This is a doubling function. We could have a tripling or a quadrupling, or we could have a decrease in the growth rate and have a fraction there. Okay, but that's generally how you would read this type of function. So what's the horizontal asymptote of this exponential function? So as x goes towards negative infinity, what's happening to the value of your function? As x gets smaller and smaller and smaller, it's getting closer to 0. And do we have a horizontal asymptote in the other direction as x goes towards positive infinity? Is there a number it's approaching? No. So we just, as x gets smaller and smaller and smaller, this goes towards negative infinity. Excuse me, the value of the function goes towards 0. So one of the things we talk about with exponential growth is they're like really like they're slow at the beginning. Look at how close this is to the x-axis. I mean, if we now took the context out of this picture and we were just looking at the mathematical function, it takes a really long time to get above that x-axis. But so your growth is real slow, but then once you start growing, boom, you take off really quickly. Okay, this is one of the sort of ideas of exponential growth. It starts off really slow and then it kind of explodes on you. Okay. So let's take a look at number 5. So here's our parent function. This is the definition of an exponential function. This is your parent function that we're going to do all types of stuff with, like stretching and shrinking and shifting and all that type of thing. But it's a pretty interesting function in the sense that now our independent variable, our variable that sits along our horizontal axis known as the x-axis generally, is now our exponent. We're used to graphing polynomial functions that look like this, x to some power. That's what we're used to looking at. Y equals x is a linear function, y equals x squared is a quadratic, y equals x cubed is a cubic. So we're not used to having our variable in the exponent spot. We're used to having it as the base. So that's one of the big differences right now, is that the base will be a positive number. Your base is always positive. B is always positive. And it can equal 1. Why can't B equal 1 here? Let's suppose I try this, 1 to the x. Why can't B equal 1? Yeah, if I graph that for values of x, if x is 0, 1 to the 0 is 1. If x is 1, 1 to the 1 is 1. If x is 2, 1 square is 1. It's a very boring function. It's just a horizontal line. So that's why we place that condition on b can't equal 0. And if you think about why b can't be negative, that's an interesting thing to look at, is to look at, you can try this later on, if you try, say, negative 2 raised to the x power. Let's just put that in for a minute and you can start to see what happens. We'll just keep our values of x non-negative here. So if x is 0, negative 2 to the 0 power would give me 1. So if I started graphing this at 0, I'd be at 1, which is what I expect because the coefficient here is 1. At 1, I'd be at negative 2. So now I'd be down here. And at 2, I'd be positive 4. So now I'm jumping up here. And at 3, what would I be? Negative 2 to the third, what would I be? Negative 8. So notice this function goes like this. It's like an oscillating function. So that's why b has to be a positive number. It can't be 1. Okay, so this is your basic definition of any exponential function. This is like your parent function that we've been looking at. It's a basic graph. So there's really 2 flavors that we can look at. with exponential functions, sort of like two parent functions here. 2 to the x. Why does it go through 0, 1? Again, whenever you look at an exponential function and it goes through 0, 1, you know you're looking at one of your parent functions because there's a 1 out here. And when you put 0 in for x, you get 2 to the 0, you just get 1 back again. If you didn't know what your base was, let's suppose I didn't tell you that this was 2 to the x, and you were trying to solve this equation for b to try to figure it out. Well, the first thing you do is you notice you have 0, 1, so you know that this isn't a transformation by stretching or shrinking b to the x because you go through 0, 1. So now you say, well, how do I figure out what my base is? Well, go to 1 and go up to see where you hit. When x is 1, whatever the value is for 1 is going to give you your base. Because look, 2 equals b to the 1. There you go. 2 is the y value, 1 is the x value, and there you go. b equals 2. So these 2 points are really very useful in helping you find your exponential function. So whatever the value is, the function's value is when x is 1, it will tell you what your base is. And similarly here, if I went to 1, look, I'm at 1/2, 1 1/2. And notice 1/2 is your base here. This goes through 0, 1. So the two flavors are an exponential growth, which for those of you who weren't here in the first 20 minutes of class we were discussing, b is greater than 1 here. B is called the growth factor. So the base of the exponential function is called the growth factor. If I put a fraction in here, then I have what's called exponential decay. And b is called the decay factor. So all you have to do to see how this works is let's put this in our calculator and just see what the table looks like. It will save us a little bit of time. So let's see what the table looks like for this. If you have a calculator at your desk and you want to just put it out and a couple of you share it, or you could watch what we're doing up here. So let's put this function in. 1/2 raised to the x. So we have 0.5 raised to the x power. Okay, and if you want to see the table, let's see, where does this graph start? Around -4 to positive. Let's do -5 to +5. So I'm going to set my table. Excuse me, I'm going to set my window. Oh, we've already got the graph. So let's set the table. Let's put it in at -5. And we're going to increment by 1. And we're going to have our calculator do all these values for us automatically. So let's hit second table. When you're at -5, which we're not there, if we were at -5, we'd be up here at 32, way up there at 32, because 1/2 to the -5 means what? You invert that 2 to the 5th, which is 32. And then at -4, you're at 16, which is about right here, because 1/2 to the -4 is the same as 2 to the 4th power, which is 16. And at -3, here we are at -3, we're at 8. And at -2, we're at 4, because all I do is invert this and then apply the power without the negative sign. So 2 squared, then again, when x is 0, this is 1. And now when I get into my positive numbers, 1/2 to the 2nd power is 1/4. So down here at 2, I'm at 1/4, and at 3, I'm at 1/8, and at 16, I'm at 4, I'm at 1/16. So in this case, as x goes towards positive infinity, the value of your function goes towards 0. So it's just the opposite of the growth function. Okay, so let's take a look at the two together. Here are the two together. We have 2 to the x, which is our growth, exponential growth function, which is the red function, and g of x is 1/2 to the x. So here they are, they're graphed on the same set of axes. What do you notice about the graphs of these two functions? If you were using some of the ideas that you learned earlier, what could you tell me about the relationship between these two functions? Yep, Andre? Has y-axis symmetry, right? Y-axis symmetry happens when we transform our function and we put the little dash where our input is. It's a horizontal transformation. And so how could we explain this? Well, let's look at these two functions. We certainly can't say they're equal, but horizontal symmetry says somewhere in my input, which is right here where my exponent is, I should see a little negative dash sign somewhere. How am I going to get that to happen so I could see why it reflects over the y-axis? Is there any way I can make this so that there's a dash here? Is there anything I can do to the base? Replace it with an equivalent idea. How about? Yeah, and could I just change 1/2 to 2 without any other change? Yeah, a dash like this. 2 to the -1 means 1/2. And now when I raise a power to a power, I multiply. So another way to write 1/2 to the x is 2 to the -1x. And there you see, I'm affecting my input into my function. It's pre-operation. This has to be a horizontal transformation, and that tells me I reflect over the y-axis. And as you can see, each one of these points here is reflected. Here's the point 3, 8, and on the other side, you're at -3, 8. That's exactly one of the properties of even symmetry or y-axis symmetry. If you change x to its opposite, your y values are exactly the same. Andre? No, they're exactly the same thing. Yeah. We don't usually bother putting the 1 in, but you could if you wanted to. You could put 1 in there. Same thing. Let me make that a little clearer. There we go. Oh, same thing. Okay, so let's come up with some general properties of these two functions, looking at their pictures here. So how would you describe the domains of these two? One's an exponential growth function and one's an exponential decay function. What about the domains? Do I have any restrictions on the domain? No. I can put any number in for x that I want. So the domain is all real numbers, which is represented this way with interval notation. Now think carefully about the range. An asymptote, a horizontal asymptote at 0, so is it ever going to be 0 in this particular case? There's no way you can get 2 to the x to equal a 0. It's just impossible. So we put a parenthesis at 0, and then how big can this get? Really big. Are these functions one-to-one? And how do we test for one-to-one? Does anybody remember? Horizontal line test, right? So if I pass a horizontal line through each of these functions, up and down, as far as a zillion of these, it doesn't matter. Oops. Right? Let me undo that. It only hits each function in one and only one spot. So it's definitely one-to-one. So why is this a good feature to have? Someone other than Andre. Why is it a good feature that the exponential function 2 to the x is one-to-one? What does that tell me about the function if it's one-to-one? Talk about it. It has an inverse, right? If your function's one-to-one, then it has an inverse. This is good news for us, folks, because if I'm trying to solve an equation like this, I'm going to put money into an account that's going to double every year, and I want to know when it's going to reach $50,000. If I want to solve this equation for x, I have to undo. I have to do the inverse. That's what we do when we solve every single equation. I have to do the inverse of saying 2 to the x. And right now, you don't know, well, maybe some of you might know what the answer is, how to do the inverse of 2 to the x. So you've got to undo it. And the good news is you can undo it, and we can solve lots of problems because this function has an inverse. Okay, but we're not going to get to that for a couple of days. All right. What about the extrema? That's relative maxes and mins, absolute maximums and mins. Any extrema on either of these functions? Nope, no extrema, none. Relative max, relative min, global max, global min. Okay, what about y-intercepts? What is the y-intercept for both of these functions? Coordinates, please. 0, 1, right. Because they're both parent functions, right? One's a parent function that's growth, and one's a parent function for decay. All right. X-intercepts. Any x-intercepts? No, we just said in the range that we can never get 0, so we're never going to cross the x-axis. None. Any asymptotes at all? Any asymptotes? And which kind of asymptote do I have? Horizontal, right. I have a horizontal asymptote for each one, and it's the x-axis, and the equation for the x-axis, the equation is y0. And end behavior, as x goes towards positive infinity for f of x equals 2 to the x, my function grows without bound. And as x goes towards negative infinity for our exponential function, we get close to our x-axis, our horizontal asymptote. And vice versa for my decay function. Everything just gets reversed. As x goes towards positive infinity, my function goes towards the horizontal asymptote 0. It gets smaller and smaller. That's supposed to be a 0 there. And as x goes towards negative infinity, my function is increasing without bound. So those, just from looking at the graphs, you could fill in all of this information, and this is all the information we've gathered over the semester. Any questions on any of this before I go on to number 9? Yeah? Yep, I'll leave it there for a sec. Okay, good. Okay. All right, so Andre's heard that one before. Okay. All right, so here we go. Here's like the same thing we've been doing with straight lines, quadratic functions, polynomial functions. I give you the graph, you got to come up with the equation. So what were the key points that we talked about in terms of trying to figure out what our exponential equation looks like? The key points we talked about was to locate your y-intercept, because 0 comma f of 0, whatever f of 0 is, that f of 0, whatever the value is at 0, is going to be the coefficient in front of b to the x. It's going to tell you if you're being stretched vertically or shrunk vertically, or if you're the parent function. Okay? Nothing's happening to you. You're just a regular parent function. The other point that we said was really important was to find the value when x is 1, because that gives you the value of your base. So when you go to the value of 1, and you then go up to your graph, whatever b is the value of your base. So let's see if we can ascertain this information. Let's find our y-intercept. Here I am at 0, 1. So this tells me I'm a vanilla exponential function. I don't have anything going on with me. I'm not being stretched. I'm not being shrunk. So this tells me I'm going to look just like this. Doesn't tell me yet whether b is positive or a fraction, but I know from looking at the graph that this is a growth. So that's another thing is it a growth function or is it a decay function? And we can see that it's clearly growing, so we know b is going to be greater than 1. So now let's find b. We go to, look at this, when I put 1 in for x, b to the 1 is going to give me b back again. So I go to my graph, I go to x equals 1, and I go up, and voila, there I am. 1 comma 5, so I know this function is 5 to the x. Okay, so just to check, you would say, well, what if I was 2? What would f of 2 look like? F of 2 looks like 5 squared, which is 25. So let me check that on my graph and make sure I did this correctly. Boom, there I am, 225. Okay. So when you're trying to find an exponential function from a graph, these are the 2 key points. But first, you for yourself, you say, am I looking at a growth function or am I looking at a decay function? So you know whether your base is a fraction between 0 and 1 or a number bigger than 1. Any questions on this? Okay, so find the equations for these exponential functions at your tables. Let's take a look at these. Does anybody come up with the function for the very first picture? Nobody? How about the second picture? Nobody? Yep, Trevor? Right. First of all, we know it's not going to have the form of b to the x because we don't go through 0, 1. So it's not going to just be a simple parent function. We see that it goes to the point 0, 4. So the question is, does that mean this is 4 times b to the x? Or could it just be a vertical shift up from the point 0, 1? So if you put 0, 1 in, and then you look at 0, 4, that's an increase of 3. So the question is, has all of my y values been multiplied by 4, or has 4 been added to all of them? So if you look at your next point, 1, 5, you say, on my doubling function here, you say 1, 5, let's see. On my doubling function, it would have been 1, 2. And if I multiply 2 by 4, I don't get 5. But if I add 3 to 5, if I add 3 to 2, I get 5. So you start to see that all of your y values have been increased by a constant right here of 3 units from your y equals 2 to the x. So in this case, f of x, your green f of x, is 2 to the x. And then you add outside your function's already happened. It's a post operation, so it's a vertical shift up of 3 units. So that's the first function. Let's take a look at the second function. Again, I go right to my y-intercept. I see 0, 3. So right away I say to myself, is this some function 3 times b to the x? Have I vertically stretched this thing from 0, 1? Because that's where I would have gone through if I was a regular exponential function. Again, I don't know what my base is. So here's my question. Am I 3 times b to the x, or have I had 2 added to my y-intercept? Is it another vertical shift? So you've got to find a second point to determine that. So what other point can you see on this graph? You can clearly see 2, 6. Excuse me, thank you. 1, 6. And you know that if this was a doubling function, it would be 1, 2. And you can see here that 2 has been increased by 6, or you could come down here and put your value of your function. F of 1 is 6, and that equals 3 times b to the 1. And if you solve for b, 6 equals 3b, so b has to be 2. Your base is 2. So this is a vertical stretch of your doubling function, 3 times 2 to the x. So sometimes we vertically shift them up and down the y-axis. Sometimes we may horizontally shift them right and left. Sometimes we vertically stretch them and shrink them. And again, we can also apply horizontal stretches and shrinks as well. So all the transformation information that you had to spend 3 days trying to internalize and learn is all going to continue to help you as you study every new family of functions. And when you go into Math 108 or Applied Calc, you'll be looking, well, 108 people will be looking at trig functions, all the same ideas apply. Okay, so this transformation stuff will be with you forever and ever. Scary. All right. All right, an irrational number symbolized by the letter E. Euler's number, Euler, E-U-L-E-R. That's where we get the letter E, Euler, famous mathematician. Appears as the base in many applied exponential function situations. It's called the natural growth rate. That's what we call B. The natural exponential function, excuse me, that's what we call E. Natural growth factor. Okay, and it's really interesting to look at E and how it's defined. We say the number E is defined as the value that this expression approaches. It's a limit. as n gets bigger and bigger and bigger and bigger. It's like a horizontal asymptote. And so if you take out your calculator and we investigate this, let's take a look at this, what E looks like. So you got to put this expression into your calculator in a Y1 button, or Y2, whatever one you prefer. I'm just going to go back to Y1. I'm going to clear out here, and I'm going to copy it just like it says. Parentheses 1 plus 1 divided by x, parentheses, raised to the x. So I'm just using x now instead of n. And in terms of business interests, this is what happens when you go from compounding yearly to monthly to daily to every second to almost every instant of time. And is getting bigger and bigger. You're taking your periods where you compound your money and you're making them smaller and smaller and smaller, which means you've got more of them. So let's see what this number approaches, what this expression approaches. So we're going to I'm going to ask my table for values of 10, 100, 1,000, and 10,000. So I'm going to set my table and we're going to start at 10. And I don't want it to automatically increment for me. I want to ask it to give me certain values. So I'm going to hit enter there. And now I go to my table. So I'm going to put 10 in and let's see. So imagine that I've put $1 into a savings account. Okay, $1. Well, we won't play the money game. We'll just take a look at E first. Okay. So here's 10. So this is what it looks like. Y1 is going to be 1 plus 1/10 raised to the 10th. So what's that look like? If this was money, it would be $1.10. That's what 1/10 is, added to $1. And you're going to do 1.10 times 1.10 times 1.10 times, 10 times. So let's see what we get when we ask the calculator. $2.59, and then we get a little more we want to keep that extra there because as money gets bigger, those third and fourth places really have meaning. So we'll keep that. What's your guess, if you haven't already done it like Andre, what's your guess at 100? What you think the number is going to be before you do it? Any guess? So now I'm going to do this 100. I said anyone other than Andre? Any other guesses? Nobody has a guess? Okay, well, let's try it. 100. 2.708. So you grew like 11 cents here. So now you have 1 plus a penny. That's 1/100th raised to the 100th power. You get 2.7048. Now we're growing. Let's see. We must get much bigger when I put 1,000 in here. Let's try it. 1,000. Oh, jeez. 2.7168. Well, what about if I put 10,000 in, which is my next value of x, right? It's growing really, let's see, 2.7181. Let's take a look at the number E, second e to the x. Oops, not here. I want to go back. Quit. Here's my E right here, second. To get the value of E, I'm going to put a 1 in there for the exponent. E to the 1 is going to give me E. And what's the value of E here, at least as many places? E is approximately 2.718281828. So you can see that this expression approaches this number E as these values of n get larger and larger and larger. So this irrational number appears as the base for many exponential functions, applied exponential functions. It's an important, if you've studied any basic math in the business area at all, you've probably have seen this formula, which has to do with money growing. P is principal, E is this irrational number we just talked about, R is the rate your money's growing, and T is your time period. I think this is an easy formula to remember because of that wonderful shampoo that comes in the green bottle called PERT. So it's always an easy thing to remember. All right. Anyway, let's finish this up. We only have a few minutes left. So here's e to the x. It acts just like all of our other functions. It's going to be e to the x is going to be between what? it's going to be sandwiched between our doubling function 2 to the x and our tripling function 3 to the x, because 2.718 is between 2 and 3. So this function acts just like the other parent functions we looked at, except for the base is not a rational number like 2 or 3, it's the irrational number e. Okay, so now what I'd like you to do, you've got 3 minutes, is here's a picture of e to the x, and here's some transformations on e to the x. Notice I've graphed e to the x in every single one of these pictures. Do a little match game here, match the equation, the function with the graph, and I'll see you on Friday.